Hello, everyone. Thanks for being here. As Dominic said, Keyla Pagán-Rivera, and I'm going to be talking about a case study on applying sequential methods to operational testing. Full disclosure, all the data is notional, as some of you might imagine. Now I confirm it. It's all notional data. None of those numbers are real. The results are, for sure. And then this is the outline that I would like to follow. First, a little bit of the introduction on sequential methods, a brief history, not too long, hopefully you don't fall asleep, then a motivating example that I'm going to use to walk through the two methods that I'm going to present, and I will wrap up with some challenges that we need to overcome and things that we need to keep in mind if we apply sequential methods to test and evaluation of defense systems. I want to start with a quote from Captain Schuyler. This is from World War II. So it summarizes why we want to know about sequential methods, and is test efficiency. He said it would be nice if there were some mechanical rule to which we can follow and know if we are able to stop a test early and answer our questions. So what are sequential methods? Most of the time, what we do for test planning is that we have our experimental design. We go some power and confidence, get the number of runs that we need using a DOE or experimental design. Then we go through test, collect the data, analyze the data, get the results, write a report. Well, sequential methods can be seen as learning on the go. So you collect certain data, or some data, and then use that information that you gain to plan for the next stage of your testing or for the next number of runs that you would like to see. And as you can see in that image, it will be more like, you test, analyze, evaluate what's your questions, and decide if you want to keep testing and analyzing, so on and so forth, until you are done, right? For the purposes of this briefing, we are going to be talking about between test event and within test events. So between test event is you refine the future testing based on previous test events. You can think of an early operational assessment, you have that test event, get your results, and based on that, you plan for your initial operational test. Or you can talk about within a test event, which will be within that operational assessment, you run certain shots or collect some data, and then within that same test event, you update the following number of runs or the conditions in which you are going to collect that data. So, many of you might know, right? Sequential integrated testing was talked this morning during the keynotes, right? It's really important. The DoD 5089 mentioned it, some of the important things of it. So it's going ahead. So we can think about after a DT or late DT, we can use that information to plan for our operational test. The same way that experimental design, the way we do it with our DOE, the traditional way, we use it to plan for experiments, we can also use sequential methods and statistical techniques, being Bayesian or being frequentist or classical, to support integrated testing. But in order to be successful, we need to keep in mind a few things. Okay, I'm not touching it. Okay, so we need to. There needs to be collaborative planning, especially if we're talking about using DT data for OT. There has to be some collaboration, there has to be some communication among all the parties involved, right? There needs to be early planning, like our test plan, like all these working group meetings. We need to talk about what are we doing, how are we doing the test, what are the decisions that need to be made, and since we're going to be updating our test plan, then we need to know who's in charge and who's going to be making the decisions and approving those changes. We need to share data early and often so we can actually make the decision and keep going. And of course, we need to train the community as to how to implement sequential methods, not only the statistical part that the methods that I'm going to show to you, but then actually on the go, like how are we collecting data, what things we need to keep in mind, how are we going to store and share the data, and of course we need to show those through applications of successful case studies. Okay. So as I mentioned earlier, Captain Schuyler on World War II, that's like, it was a long time ago, this is nothing new. And it was for an anti-aircraft gunnery that they wanted to test. And he said, well, someone with my credentials, he was a captain of the Navy, so he thought that someone with his credential, his experience, should be able to know, like, when are you supposed to stop testing and see if this system is good or is not good, right? So there comes the statisticians, in this case, Abraham Wald. So he developed the sequential probability ratio test, which is the first method that I'm gonna show to you. And that was pretty much to see, like, okay, binary outcome. Is the system good? It is not good. And then we can keep testing until we are able to make the decision of stop collecting data, answer our questions. This was a fun fact. World War II, the method itself was classified because we were in the war, so it was declassified until 1945. Okay, fast forward, 1998, the National Academy of Sciences put this report that the OT&E sponsored on the benefits and the challenges of using sequential methods. The thing that I have been saying, I guess, from the very beginning, it will be good if we use sequential methods. It's good for test efficiency. Maybe we can save resources, save time, but you might be wondering, why aren't we applying this right now? And in that same report, they were already pointing out some of the challenges that could be seen if we apply this in T&E. And if you remember nothing else from this talk, please remember this. Yes, it might be tough. Yes, there are challenges, but that doesn't mean we should not be trying to implement this and try to take advantage of these methods. So, okay, history is over, right? Background is over. So how can we actually implement this in T&E? So this is an example. Yes, Laura, this was your example from IOT&E in 2015 that the Army did. So long story short, the Q-53 can detect incoming artillery, a mortar and radar. It's a radar, and it could actually detect them with certain probability, and it can also detect the origin of that shot. We are going to focus the first part on that first question, like, can the Q-53 detect the shots with high probability, right? So we want to know if the failure rate of the Q-53 is what we think it should be, or if it's worse. If it's worse, then it's not good for our soldiers, right? The traditional way of doing this is like you have your hypothesis. It could be this is the failure rate, or it could be something else. Collect your data, compute your p-value, and then you decide, yes, I reject the null hypothesis, the Q-53 is better, it's not, or write your report and keep going. Now, if we use the sequential probability ratio test from Abraham Wald, then we still have the same question. We still want to know if my radar is good or is not. But now we're going to have that S, which is my test statistic, and I'm going to update that S as I go in collecting data. I collect data, compute my S, my test statistic, and then I make a decision. So if my S is larger or smaller than my boundaries, the R and the A, then I can stop testing. If it's in between, which is the second bullet there, then you just keep collecting data until you have enough data, enough information to actually answer your questions. What does this look in action, like if I have just the one test? You're going to see in this, let me first orient you. You have the total number of failures, that's cumulative on the y-axis, and then you have your sample number. First shot, second shot, third shot, so on and so forth. And then we compute our acceptance and rejection regions. And then I'm just going to start getting some data. And I collect data, nothing happened, right? I keep going. And then after the fourth shot, there was a failure. So I update my test statistic. Since I'm still within the boundaries, I'm like, okay, let me keep collecting data. So I keep going, right, until I go outside of my region, and then after that, the 9th shot, then I said, okay, I have enough data to reject my null hypothesis, and voila, I can write my report and say that we could reject our null hypothesis after 9 shots. With non-sequential methods, you need to actually, collect all the data before you can actually make a decision. This is with just one test, just certain conditions. What happens if I run this test many times, right? So I'm going to have a simulation study. Does it really work? Can I actually do this and control for error? So we have our 2 types of error. We are using the exact binomial test as the non-sequential method. And we can see that the error are similar in both cases. Like when I'm rejecting my null hypothesis, if I reject my null hypothesis when I'm not supposed to do it, or if I accept the alternative when I'm not supposed to do it, those are errors that I'm making there, and they are about the same. Now, in terms of test efficiency, that's the sample size. For the non-sequential, we are always going to have our power and sample size calculation. I have a fixed number of runs every time. Now, for my sequential method, every time I have a run, I am updating my plan. So that's why we're talking about the average sample size. So it could be a little bit more, it could be a little bit less than the 20 some runs that I'm showing there, but on average, I am using less runs with the SPRT. And now you might be thinking, well, I took the experimental design short course on Tuesday, and they say that we have factors and levels and things that could affect the performance of the radar. So yes, there are things that could affect that, and I have them in the table. I'm not going to read them all for you, but they are there. So there are many factors and levels, some categorical, some continuous, 2 and 3 levels each, and we want to know if some of those do affect the performance of my radar. We can have simple model with just the main effects. We can have the main effects and interactions, which means that the performance of my radar might depend on a combination of things, right? Or we can have quadratic terms, right? So since I know nothing, I'm just going to try to fit the most complex model. So if we plan the traditional DOE approach, we can have a full factorial design. There's a typo there, it should be 400 and some. So sorry about that. So we want to characterize this. And we're going to have the main effects, the interactions, and the quadratic terms. And I'm testing everything, every possible combinations. And again, that's not supposed to be 96. Okay. And then you can think like, well, I can optimize this, and I can have an optimal design, so I can have less runs. For that, you need to assume that you know what will be the model and then collect some data. Again, I have the main effects, interactions, quadratic terms, and I'm going to say like, well, I'm going to have 184 shots. So this is the traditional way, non-sequential. So what if I do a sequential approach? So we have this method that we can do it in phases. The part that I'm showing right now is 3 phases. So it will be, phase 1 will be the salmon color, phase 2 will be the green color, and then phase 3 will be the blue color. It could be within a test event that you split your shots in a certain way, or it could be between test event or among if you have more tests. And here are the details about each phase. For the first phase, I'm just doing a screening design. I do my experimental design, assuming that I just want to see if there are main effects that are important, that are affecting my the radar performance. I do the DOE, collect the data, fit the model, make a decision. Should I keep collecting data? Can I stop? If I decide that, or my data says that yes, I should keep collecting data, then I go to the second phase. So I'll augment and include interactions in this second phase. Once again, I use an experimental design, decide where I'm going to collect the data, the order that I'm collecting data as well, that's important, and then collect the data, feed the model, answer the question, should I keep going or not? And the last phase will be adding quadratic terms. And you keep going. So does it work? Once again, if I do this many, many times in the long run, will it be good, right? So we did another simulation study. In this case, we have our most complex model will be model 1, main effects, interactions, quadratic terms. Then model 2 will be the main effects and interaction, and model 3 will be just a simple model with main effects. And then we have different simulation settings. The optimal design for the non-sequential, 1,000 data set for each of these experiments. And then different variability and confidence, which are the alphas for each phase. We start a little bit more conservative in saying, well, instead of like 80% confident, then I'm 70% confident on phase 1, and then 85 for the other 2 phases. So let's see if the simulation stops where it's supposed to stop, right? So for model 3, I want it to stop at the 3rd phase. I want it to go all the way through because I want to collect all the data up to quadratic terms. And as you can see, based on the simulations, most of the time it did stop at the 3rd phase. Of course, when there's more noise, when the standard deviation is higher, and more variability in the data, you have only 76%, but it's still good for this method. So for model 2, I want to stop at the 2nd phase when I have the main effects and the interactions. And in this case, it's 85% or more of the time I am actually stopping at the correct time. And for model 3, which is the simpler model, I want to stop at the first phase, after the first phase. So if I collect data, phase 1, say I need to stop, then about 90% of the time, I'm right at stopping right after phase 1. Back to test efficiency. What does the sample size looks like? So again, these are the results from the simulation. And it shows like even the first 3 bars that are in red, those are the complex model. So the gray ones is the optimal design, and that will be the average sample size that you have on your y-axis. On the x-axis, you have the models with different types of variability. And you can see that if you do this sequentially, even for if the true model is the most complex model, you are still running, stopping the test with less runs than with the non-sequential. And again, this is on average. There could be times where you might go like a little bit more runs or less run than what I'm showing in here. This is just the average. An important caveat here. Again, I am assuming that I know nothing about my radar, so I want the most complex model. But if I have a subject matter expert that tells me there is no quadratic effects, there are no interaction, just main effects, then my sequential method might be asking me to do more runs than the non-sequential. So it's a matter of like keeping in mind what are the conditions, what do I know about the data, and then from your toolbox, use the tool that works the best for that situation. Couple of challenges. If you're doing sequential methods within a test event, then there needs to be real-time planning, analysis, data collection. There might be updated to the test plan. We need to know who's going to approve those changes. Of course, there could be some people misusing it, doing like p-hacking. We need to know if I am collecting data at this range right now, but then tomorrow I need to collect data at this other place. Can I get on their schedule and run my set of runs? It will be a little bit similar when we are doing between test events, but here we're also adding the fact that, well, there might be competing goals between the developmental test events and the operational test events, and we need to keep that in mind. Did the system change a lot between the DT and OT, right? And again, challenges do not mean that it is not doable, just that we need to keep all of these things in mind when we are trying to apply sequential methods. So what does all of this means for OT, right? So applying sequential strategy might help save resources, save time, reduce the cost of runs, as I showed you on the plots earlier. But of course, we need to get access to the data, schedules, people, resources need to be flexible, and then there has to be close collaboration among all the involved parties. And that's it. Questions?
If there's any questions from the audience, please. Microphone.
Yeah, so when you're dealing with multiple factors and you're doing some sort of sequential design like this, where you have different phases, I'd worry about introducing some sort of conflating factor on accident. How do you deal with randomization? Do you randomize fully across the different phases, or would you do some sort of blocking technique where we'd have each phase fully representative of your factor space?
So the way we did it for this specific example, randomization within each of the phases. And then within each phase, you're going to have your regular experimental design with certain confidence and power, and then there is a randomization within that same area. And then just, augment the design.
Thank you.
Hello,
Hi.
Max Thompson, Affotech. I was curious whether your D-optimal design was based around the fact that you had already done a screening design and taking those data points into account, or whether the D-optimal design was built without regard to the screening design.
So the optimal design was created as our non-sequential method. And
Okay,
yeah.
gotcha. What was the design type for your stages 2 and 3?
I think was the screen? Yeah. So yes, sorry. So there was the optimal, but it was within each of the phases.
Okay,
So it was not taking into account the other, knowing that we could have more
Gotcha.
phases data that we're going to collect. Yeah.
thanks.
With the methods to determine when you would reject or fail to reject the null hypothesis, I think it was the R and A. I was surprised to see the lines were parallel in that, well, theoretically, if it were at just the wrong value, you could go for a very long time without making a decision. I was wondering if there might be methods in which those two eventually converge to where R is A, where there would be a decision by a certain point if you hadn't reached one yet.
Not that I know of, at least for the SPRT, but at some point, of course, if you have 50 shots and the resources for your test, you run out, then you have to stop. But for this specific example, they were like that. And you're right, there could be situations depending on how you set your hypothesis and your confidence and all that, so that you can go forever, right, and not make a decision, and then that's when the non-sequential might be doing best and having less runs.
Thank you.